And here's your, whatever, I think 2.4K, which doesn't matter. There's V in. And here is 750 ohms. And here's V out, right?
That's what I did too.
Right? Now, split this impedance reflection. You get a resistor here, which it doesn't matter. And this resistor will be what? 50 times beta plus 1. Right?
50 times beta plus 1.
Right? Now, V out over V in is V out over IB.
Times IB over
IB over V in.
VB.
Right?
IB over VB. And then
Oh, okay.
VB over
V in is V. Well, I don't need VB. V in.
Yeah.
That's V in right there. This should be minus beta 750 divided by R pi plus 50 times beta plus 1, right? Now watch this. Divide beta on top and bottom, you get minus 750. What's R pi over beta? Huh? R pi over beta, little RE. Right? Because if you divide this by beta, here's the answer. R equivalent in the collector, divide what is in the emitter, little RE plus the 50 ohm. That's what I put here. And that's approximately 10. If you know, beta plus 1 over beta is 1. So slightly less than 10. If you, but it's 10 because we already ignored that part.
So I'm multiply negative B times 7.5. I literally did the same thing, but I think I messed up some numbers. So I calculated R pi. I didn't assume it's RE.
So what? You should get minus 10. Okay,
I said
here's 100
so
times 750
That's,
divided by
no, so
R pi is 2.5K plus 50 ohms. Right?
So what I did is I used
No, this is
times VT. So beta times VT over ICQ. Okay, that's why I got different numbers.
just a second. 200, 2.5K plus 5K. Right? R pi is 2.5K.
So R pi is equal to beta VT over ICQ.
Right? What's the answer there?
Does R pi always equal to RE or
That's what?
R pi is equal to RE or in different cases maybe?
It's R pi divided by beta is RE, right?
That's right. It's not equal RE. R pi over beta is RE. Okay. How many got 10? I gave the same lecture, and I'm going to give it to you, to the other class. You guys don't study till you are step on your tail. You got a quiz, you start studying. You're not going to get this material this way. You got to make the mistakes, solve problems beforehand. You know, we solve them here, you depend on me solving the problems, but you're not doing it at home and making the mistakes to find out where your mistakes are. If you don't do that, you're not going to get it. Okay? If I twist any problem a little differently, which is, there's one problem, it twisted a little differently, we won't get to it today. And it was a test problem. If you don't solve it at home and work it with it, it's hard to get this material. So don't wait till the day you have a quiz or you got a test coming up. Steve, you feeling better?
Somewhat, just it's more stress than anything.
Did you guys have a big accident of some sort?
Yeah.
Wow.
It was a hit and run. They totaled the car and
Nobody got
the
hurt,
people
right?
that hit us ran off, so we had to get attorneys and everything. So,
Did you catch them?
No.
Your insurance will cover that.
Well, the insurance says because it's a hit and run, they don't want to pay anything, so we have to. I got an attorney to go after the insurance company.
What kind of insurance is this?
Insurance companies suck. That's what I'm finding out.
You have to have uninsured motorist.
But I have uninsured motorist, but they didn't give it to me for property damage. They gave it to me only for medical.
That's I hate insurance companies.
Yeah, they're screwing with it.
Insurance company, medical insurance company, any insurance company, they're a bunch of crooks.
Yeah.
That's what I'm
They're
finding out.
liars.
Yep.
They read the fine print and they create more fine print that you don't see.
Exactly. Yeah.
This country is gone to hell.
My attorney's confident we'll get money out of them, but it's just
It is. I mean,
yeah.
God forbid you get sick and go to the hospital and see what happens.
You go bankrupt.
Huh?
You go bankrupt.
Yeah. You go bankrupt.
Yeah.
And then you go to the doctor, he'll see you 3 minutes. 3 minutes. I went to orthopedic guy 3 times, okay, for my knee. I twisted my knee and popped the meniscus there. I swear to you, I was in and out of there. They made me wait an hour and 15 minutes. I saw the doctor for 3 minutes. $450. No, I didn't pay, I paid my deductible. But that's the bill to the insurance company.
Yeah.
And I knew everything is wrong with me because I read the damn book. What's going wrong? And they did MRI. I saw the pictures of MRI. I could tell you what's wrong. Doesn't take a genius. $450, and they don't do anything. Doctors don't do it today. They don't do anything anymore. All they want to do, get you in and out. I went to my allergist. I hate that guy. Now I'm going on a tangent because I was there 2 weeks ago. I take allergy shots at this age. I should have done it 50 years ago. I went there, said, the serum is expired and you need to see your annual doctor because they will not renew the serum. Okay, I hate to go to him because he's lousy. Okay, he comes in, they have your patient chair facing the wall. I mean, between you and the wall 3 feet. His computer is behind you. Okay, he comes in, you don't see him, he's talking behind you. And said, okay, I guess we need to do this, to this, to that. All right, and then I'll see you next time. I swear to you, I didn't see him probably 5 seconds. He was there for 3 minutes, but I didn't see him 5 seconds. He came in my face. He looked in my ear. He can't find. He said, look up my nose, like a split of a second each time. I said, how can you find what's your inside the ear in a split in a second? The light hasn't gotten there yet at speed of light. He went out there, and then he goes and right away sits on the computer to write the report. It's to the insurance, Medicare.
Yeah.
Then I went to the allergist 2 weeks later. He said, oh, we haven't gotten the report from them to order the serum. This country medical business stinks. The insurance business stinks. That's why I believe in Bernie Sanders.
Oh, very good.
They got to do something. Well, they don't do something, you know what's going to happen? It's going to collapse.
Yep.
It's going to implode on its own weight. Then people will rise and will elect the right people.
Or they'll suffer.
This is not the political science class, so we should go back to engineering. you can tell my political views, right? Very liberal. And you find that in colleges anyway, among college students and college professors. They are very liberal kind of, except engineers. The engineers tend to be very conservative thinkers. I'm not one of them, but engineers are. Okay, let's do this problem.
Did you get -10?
All right. We're saying beta is infinity. Calculate the operating points for both transistors. Where do you start?
Q1.
Huh? Q1, where? First of all, let's take a look at Q1. If we're going to calculate the gain, there are two sorts of amplifiers here. The front, talking about AC now. This is -5 volt here. The input transistor is what configuration? Common base, common emitter, common collector. Common base, right?
Yeah.
The base is common, it's ground. How about the output?
Common emitter.
Common emitter. Okay. Let's start here. What's this voltage? Right? What's this voltage? DC now. I say ignore base currents like I did in the quiz. What's this voltage? Minus 0.7.
Oh, yeah.
Now, what's this current?
It's -0.7 plus 5 over 2.15.
What is it? This current is will be IE1 approximately equal IC1, and it's equal minus 0.7 minus -5 divided by 2.15 K, and that is 2 milliamp. If that's 2 milliamp, what's this voltage? 1 volt, right? So what's Q1 operating point? 2 milliamp. And what's the current? What's the voltage? 1.7 volt, right? 1 minus 0.7. Okay, this is 1 volt. What's this voltage? 0.3, right? And this is -5. What's this current?
0.3 plus 5 over 4.7.
So, 1 milliamp, right? 4.7 volt over 4.7 K. Oh, they came, okay. 1 milliamp. What's this voltage?
It's 5 minus 2. That's the 3.
So what's the Q point for this?
3, 1.
1 milliamp.
2.7.
Oh, yeah.
2.7 volt, right? Now it's easy. That's two-stage amplifier. Now let's do AC load line on 2. What's the DC load line? We have 10 volt is equal I sub C 2, well let's call it IC2. What's the impedance for DC? 2K plus for both of those, right? 6.7K plus VCE2. So you plot this, you get 10 volt, and you get this to be 10 divided by 6.7, okay, it's 1.5 milliamp. And the Q point is here. 2.7, and this is 1. Right? Now the AC load line. What happens to this resistor? Shorts. This is dead. This is dead. 4K in parallel with 4K becomes 1, right? So the AC load line is going to be IC total 2 minus 1 milliamp times the impedance across, which will be 2K in parallel with 4K plus VCE total 2 minus 2.7 volt equals 0. Everybody understands where this comes from, right? From the AC equation, do you know?
Yeah.
Okay, let's do the AC loop here. This is ground. This resistor 2K in parallel with 4K. And that's a ground. Right there, you'll have I little c times 2K in parallel with 4K plus V little ce. That can be IC total minus ICQ, which is 1 milliamp. This combination is 1.3K. This will be VCE total minus VCEQ, 2.7 volt. Okay? That's that. You plot this. This is 1.3. Okay. You get this intercept approximately 3.1 by setting this to 0. 2.7 divided by 1.3, approximately 2.1 plus 1. 3.1. And this would be 1.3 plus 2.74. So it goes like this. This is 4 volt. That's your Q, the DC load line. So this can swing plus or minus 2 volts, 2.7 volt. Without clipping. If you overdrive it, it will clip, and this easy bit. This circuit very easy to overdrive because it's very high gain. All right, now I need somebody to draw the small signal equivalent circuit. What happened to my muscle in my back is all of a sudden. All right, who's going to do that? You are? Come on. Look, this is common base in the front. You can do it common in pi model, you can do it T model. Common base is very good to do for T model. Okay?
So what are we doing?
T model. Put the T model in the front and pi model in the second. It's much easier it's not V, a little, oh, little
oh,
RE, yeah, but not big E, little RE. That's from notation. Now the emitter is tied to Vin and 2.15K, right? All right. The collector goes into the second stage. That's a ground. And then you have the 2K on the front between the two, right there in the first circuit. You have 2K on the collector, you have 2K, that's the load, right? On the output, you have the 2K in parallel with 4K, 1.3K, right? All right, now designate your currents. Beta IB1, beta IB2, this is IB2. This is 2, this is IB2, and this is RPI2. Okay, and this is beta IB1. And the bottom one, that's it. Okay, now write the chain. To IB1. There you go. You got the right chain, right? Okay. You understand that chain, where you coming from? Okay. Continue. That's the first ratio. Put it in parentheses, that's the first ratio. The second ratio, look at it, the second ratio, current over current, that's current division, which is equal the current going out, so it's minus beta times 2K 2K plus R by 2. Okay, and the last one. What's the current in RE? Beta plus 1 IB, right? What's the current? And put beta plus 1 IB through RE. Beta plus 1 IB1, right? Okay, we're looking for IB1 to Vn. Look where Vn is. The 2.15K doesn't do anything, right? Okay, here. Write it on the front. 0 minus Vn over Re, all over Re, little re, equals beta 1 plus 1 IB, 1, right? Right?
So the current equal to the different voltage over the resistor.
That's Ohm's law. Okay? Now I'm looking for what? IB1 over Vn. What do you get? IB1 over Vn, write out. Over there underneath it, IB1 over Vn It's equal to minus 1 over RE times beta plus 1 on the bottom. Beta plus 1 on the bottom. Yeah, put the parentheses there. Okay. No.
Above parentheses between P.
RE plus beta plus 1. No. RE times beta plus 1. I'm sorry, yeah. Okay.
Yeah.
Which is equal 1 over R pi. RE times beta plus 1 is R pi. You don't have to do that.
but
Well, you can
so-
do that, okay? Do it. What's RE times beta plus 1? R pi. We just talked about that, right? So the answer is 1 over R pi. You don't have to do that, but you could put it to 1 over R pi, and you're done.
We say that because
That's how
beta
RE
plus 1 is
the
for faculty just beta.
1, yeah. You don't have to do that. You could put beta plus 1 RE. Actually, it's easier. I'll tell you why. It's easier to put it the other way. Beta plus 1, R little e. This goes out with that.
Yeah.
Okay? Little RE, this is the current. What was the current at the output? 1 milliamp? 1 milliamp?
Hmm.
So this is 25 ohms. So you're going to have minus 100 times 1K, 1.3K, divided by 25, that's 25, and that's 2 divided by, times 2 divided by 4.5. That's the answer.
Now, why do we bother solving the entire thing there whenever we just have the AV equation and we can just cancel out IVs?
I don't understand the question. What do you mean? How are you going to find V out over V in?
Yeah, I guess that's fair.
You cancel them, you're going to end up with V out over V in. How do you find those?
That's
We're finding fractions that
right.
multiply and fractions give you that.
Mm-hmm.
Right? Let's see if I could add more knowledge to your class.
I have so much catching up to do this weekend.
I don't know what the answer is. Look, it's very high. So they give you 1 over, what's that if you multiply? What's the answer, somebody? It's very high in the 4,000. It's a 2-stage amplifier. Nobody's trying to help me, huh?
Yeah, I'm doing it now.
You're doing it?
Wait, what?
I got negative 2,311.
2,300?
That's what I got.
The other guys told me 4,000. 2,300? Is it in the book 4,000 or 2,000?
I don't know.
Because we're correcting the book, so.
Yeah, negative 2,300.
Yeah, 25, this is, this is 40. 40 over approximately 10. I don't know, is it? Whatever. Okay. Are you comfortable?
Not yet, but we'll get there.
You're working on it.
Playing catch up.
We did the T model here, yes.
So that's a RE there?
Yes.
It's negative 4,000 in the book.
Like, how does that work? So
That's the
RE
T model.
equation is RE?
Do we have different input values than what we have here?
This one is the T model, not the pi model. All right? I'm going to do it with the pi model now. All right? I'm gonna erase this. And here's the pi model. Right?
Okay.
Right?
And that VI is no longer part of it there.
But there's the end right there.
Oh, okay. I see.
Take a look here. Vn is equal to something IB. What is that? This is Vn, right? Vn connected here.
Yes.
This is 0.
Yes.
What's this voltage in terms of IB?
V minus V.
Minus IB R pi, right? Is that right? IB1? R pi 1? You see that or not? Okay, because 0 minus Vn divided by R pi 1 is equal IB. Okay, now let's go back there. V out over Vn is equal to V out over IB2, IB2 to IB1, IB1 to Vn. V out over IB2
Just whatever our pi.
right? And this is minus beta, 2k in parallel with over 2k plus r pi, which is, r pi 2, which is 2.5k. That's where the mistake I made, I think. Right? We made a mistake here. That's why you get 4,000. This is RE1, which is 12.5 ohms. 12.5, not 25. That's where the mistake this is 25k. Now, I do want to be in right there.
So you're saying the book was correct, or what we did
The
was?
book is correct.
Okay.
What's V? RB over Vn? Which is the same relationship. And this one, I said, this one, instead of 25, is 12.5 ohm, 1.25K, instead of 2.5K. And this would be 4 over 4.5, right here. And that should be, well, you take this beta, put it here, it'll be 12.5 ohms, times, that's 1 over. Okay, and this would be minus 100 times 1.3K, and the answer minus 4,700 something. Right. Twice what you got. Twice what the error we made here. Okay. See, you're solving complex problems now. There are two-stage amplifiers here. And it's very high gain. You cannot, in other words, if you build this in the lab, you have to put a very small signal in the input. Otherwise, it's going to clip like hell, because 4,000 times 1 millivolt, you put 1 millivolt sine omega t, what are you going to get on the output according to this problem? Huh?
Said a lot.
4.7 volt
Yeah.
8.7 volt peak to peak. It's gonna clip like hell. Why? We
just
erased
got rid
it.
of our graph.
It's only can swing 2.7 up and 2.7 down. So you gotta put less than a half a millivolt to see the AC signal, because this is a high gain, right? You put 1 millivolt in, it's gonna clip. It's gonna go too high and too low, because it's gonna go to 4.
Isn't it just 1.3 up and down?
Yeah,
sorry.
1.3 up and down.
2.7
And 4.
No, I was 1.3, yeah.
Yeah.
See, if you put 1 millivolt in, theoretically, and it's negative, right? No, it's positive. Was it negative or positive?
Current? It's 1 milliamp.
Is it positive?
Yeah.
No, I think it's negative, right? Whatever. Suppose it's negative. Well, this is negative, the other one. No, it's positive. So the other one, supposedly, if this 1 millivolt, it's gonna go, that's in volts now, 4.7 volt minus 4.7 volt. It can't do that. It's gonna clip right here. And this is IO. If you put 1 millivolt, it's gonna look like this on the output. So you gotta cut down your input voltage is extremely high to a quarter of millivolt, 25 microvolts sine omega t, then you see it. This is in microvolt, this is in volt. So you can't really draw it here. Okay. We talked about impedance reflection from the base into the emitter. What happens if you look from the emitter to the base? This is actually the problem we just did. You need to understand this part, because when you get into electronics too, and you have to do circuit analysis for frequency response, you better be good in impedance reflection on the spot. Okay. This is AC equivalent circuit, and I have RX here. What is the input impedance looking this way between these two nodes? What is R Thevenin? Somebody come up here, do it. How do you find input impedance for anything? You apply test voltage, you measure the test current, is VT over IC, right? VT over IT. Come up here, you help me. Yeah, no, you.
Right.
What? I can't do Thevenin. No.
Come on, man.
Thevenin gave me like.
I'll help you, okay? Erase there.
Okay, that.
And here's a chalk even, I'll help you with that. No, erase there. Some of you have been going to Dr. Ebon for help? He's a good guy, go if you can.
Help with what?
With the electronic.
Oh, I've still never met him.
Yeah, he's a very nice fellow, he's very helpful.
He's doing electronics too.
Yeah, he's teaching electronics too. All right.
Okay.
I used to teach electronics 2 and 3. I'm not teaching that anymore. All right, how do you calculate input impedance? Or impedance of anything? You put the circuit, you apply test voltage, and measure test current, and VT over IT is the input impedance, right? Draw the small signal equivalent circuit for this. The input impedance is an AC phenomenon, not DC.
Yeah.
Impedance is AC, and that's why I drew AC here. I put grounds up there and a connect. All right. Grounded, doesn't have to be. We could put the resistor if you don't want, okay. Put the rest of the circuit in.
Something goes here.
Okay, no, that's not.
This is ground, right?
No, no, it's not ground, it's open.
It's open?
Yeah, see, this is R pi.
This is our spot, okay.
This is R pi. Put R pi,
Put it.
swiggle,
Resistor.
put the swiggle.
Resistor.
Like that.
Okay, put the Rx where it goes. It goes on the emitter, no.
Oh, okay.
Right there, Rx,
Okay.
to ground, put the swiggle to ground.
Put the resistor.
Okay, now, that's beta IB, and take that other ground on the input. Take it off, all that line. All right? Put beta IB on the current source, Here, IB there. This is IB. I put the arrow. Okay? Beta IB on the current source.
Going down.
Down here.
No, in the current source for the model.
Inside of it.
The transistor
Diamond.
model. And that little square.
Inside the
Yeah,
diamond.
yeah.
Beta IB, right?
Okay.
I'll put it on the outside and put the
Into
arrow.
that direction.
Direction's up, right?
Oh,
No,
it's
it
down.
doesn't.
It's down.
It's
Down. Beta IB. That's the model. You did this on the quiz, right?
Yeah.
Now, I'm gonna apply a test voltage, VT. Apply a test voltage, look what it is.
Okay.
Yeah, from there to ground is VT.
Okay.
VT, yeah, put a node to ground.
What's the resistor?
What's your name, Ryan?
Yep.
Ryan.
I see what you mean.
You're looking this way. Rn. VT over IT. That is from circuit 1 or Thevenin. Okay, find that. Are you escaping?
Do you want me to solve this? Okay.
What's VT equal to? You know, I need a lady up here. We haven't asked the ladies to come here, except for the one that is sick.
I'm not late.
No, you're not. Taylor, come here, Taylor. I know your name, I don't know the other lady's name.
I'll stand up here.
No, you know it.
Oh, all right.
I like the
VT,
confidence.
do KVL.
Where's the waterfall? All right. Doing KVL here.
Yeah, do KVL, VT.
All right. So
You're better than you think.
Oh boy. All right. So we're going to
VT equal
equals.
IB R pi, right? Plus beta plus 1 Rx, right?
And little RX.
No, the big Rx right there. See it? You understand that KVL?
I see it. Yeah.
Okay, now what's IT equal to? Equal to IB, correct?
Yeah. So IT here. equals
Okay, now, beta plus 1 IB Rx. You left IB out. Second term. There got the IB. Now factor. Okay, now factor IB out on the first equation. IB parentheses R
Little
pi
R pi, right?
plus beta plus 1 Rx, right? Okay, now this is equal to VT. Okay, look at the circuit, VT equal to IT, correct?
VT equals IT.
No, there, look up there. Up there, where I put IT.
Yeah, up here.
Yeah, it's equal to VT, equal to IB, right?
Yeah. equal to
And
IT.
I'm looking for VT over IT, this is Rn. So take the IB out and put IT on it. Equals VT, right? Okay, now VT over IT
Is yep.
This is will be equal Rn. It's equal to R pi plus beta plus 1 Rx, right? That's the impedance reflection. That's the input impedance, right? Okay, so you know how to do it. You just, you're not
Confidence is key, right?
Yes. Confident enough.
Confidence is key. Confidence is key.
That's right, yeah. You wanna try this one?
Oh, if you're, I mean, if,
How about this
do
one?
whatever you want.
All right, try this one.
All right.
And here's what we're looking. Rn this way, there's Vt, and there is It.
All right.
So we're looking now at the transistor in this direction, from there to there. And what do we see? See, we looked from this way, we saw R pi plus Rx times beta plus 1. Now looking up the emitter, what do you think you're going to see?
Yeah.
You're going to see Rx in parallel with the little Re, because this has little Re to ground. With the T model, it's very quick. With the pi model, it takes a little bit more work. But it gives you the same thing. Do the T model and I'll do the pi. Here, I'll help you.
Yeah, yeah.
Beta IB, little Re, this is the T model, right?
Right.
And here is Rx. And here is the connection Vt, and here's It. And that's ground. That's easy, right?
Okay.
Oh, the pi, that's ground. This is some resistor to ground. Take a look at that. What do you see?
Oh, you asking?
Yeah. What do you see? You don't know what you see.
I
Let's
see a circuit.
Yeah, good. But look where the ground is.
Right.
From the node you're looking at to RE.
Right. So
Through RE, right?
Oh, so I look through
Okay.
RE. Right. So
Yeah. From that node up to through RE.
Right.
And then from that node through Rx. So essentially, what is Rn?
Rn.
Yeah, the one I'm calling this Rn.
Voltage division.
What's the impedance looking this way? Is it the same thing as this? Is that the same thing? That's right. Okay.
Yes.
Right?
I
You
see.
see it now?
I see.
So looking up the emitter, you see little Re, and it will be in parallel with Rx. Okay, this is the T model, which is simple to see. I'm going to do it with pi model.
Perfect.
I'll save
Wonderful.
you.
Thank you.
Thank you, Dad.
Of course.
Let's do the pi model. This is the pi model. Right up here, right? And I'm looking here. Let's do KCL right here. Okay, this is IB. Let's do KCL. I sub T coming in plus I sub B coming in plus beta IB coming in, this one, minus Vt over Rx equals 0. Right? This is Vt, the ground. So Vt over Rx equals 0. Right? Okay? Let's take a look at Vt. This is Vt. Remember that line is Vt. You can see Vt is equal minus IB R pi. Is that right? This is IB. There's a ground. IB R pi is equal minus Vt. Right? So I'm going to take this IB out and put instead Vt. So I'm gonna have IT here minus VT,
It's R pi versus VT.
sorry,
R pi
minus
over
beta
VT.
plus 1. It's actually plus beta plus 1. IB, which is minus VT over R pi. Minus VT over Rx equals 0, right? Right?
Mhm.
No? You don't see it? Okay, you can write this one as beta plus 1 IB, right? Right? Okay? Now I'm going to substitute for IB. What's IB equal to? VT over R pi, right? They better be the same sign or we're in trouble because impedance cannot be 1 minus something, right? Something minus something. But you can see they're both minus. So you're going to have IT is equal to VT 1 over beta plus 1 over R pi. Is that right? Plus 1 over Rx. I got, right? Okay? Now I'm looking for 1. What's beta plus 1 over R pi? Right? This is Rn. What's this? Right? Yeah? Rx plus Re over Rx, Re, flip it around and become in parallel. Which what Taylor got, very simple with the T model. But the pi model gets you there.
Mhm.
So, if you're looking up the emitter, you see a little Re. Down the emitter, you see R pi. You see a little Re, whatever in the base, divided by beta plus 1. In other words, if there was something here, if there was something, say Ry, this will be R pi plus Ry divided by beta plus 1 in parallel with Rx. You see what I'm talking about? Looking in here, you got R pi divided by beta plus 1. You add one more impedance, so what? It'll be added to R pi, so it'll be Ry plus R pi divided by beta plus 1 in parallel with Rx. That's the impedance looking through the emitter. It's much lower impedance than looking through the base. Okay. You got one more lecture. There's that fancy problem I will do.
Thursday
Then-
before the exam, are you going to be lecturing?
The exam, I don't know. That's the problem. I wish they'd put the solicitation after,
Yeah.
not in between.
Yeah.
Because you're behind one lecture all the time. So I don't know. And you see, we cannot do exams outside Thursdays. I don't want to make 2 exams because it would be unfair. I may make one harder than the other. Oh my God, today nobody called me. Who's calling me now? Oh, my
It's your
sister.
insurance company.
No, that's my sister in Texas.
Okay, well,
I know what she does. She's driving from Fort Worth to Dallas. She always calls me on the road to keep her busy. So, she's a really mess.
Thank you, Professor.
I got a hell of an older sister. You look at her, she looks like 70 years old woman. She is 84. She's been around the world. I mean, when I'm saying around the world, she has been, and she never sits still. And this Christmas, she's going to Dubai. She just came back from Lebanon.
Oh.
She crosses the Atlantic like it's nothing.
Especially
She's
at that
been
age, yeah.
everywhere, Russia, China, South America, Chile,
What does she do?
all over Europe.
Just travel, or?
She travels, yeah.
For
She's
fun or work?
retired. Her husband was,
Sure, she's
it
retired,
was, I mean, but he's still alive. He's 89, and she's knocking the hell out of him. He told me they travel now since business class. He said, even with business class, you get tired sitting in the plane for 15 hours from Dubai all the way to Dallas, Texas. But the poor man, he can't say no because she's very strong-willed. Her daughter lives in Dubai, so they're gonna go for Christmas there.
Do you ever go with them?
Yeah, like every couple of years I go to Dallas to see them. They may be coming in October.
But you don't like go on any of the exotic trips with them?
No, hell no. I can't keep up with them. She's very sweet. I have 3 sisters. They're all limping. All right, guys. I'll see you on Tuesday.
All right, January.